Thank you for the opportunity to speak at this virtual Nanoscientific Symposium. The title of my talk is AFM with Nanoscale Vis-IR Spectroscopy via Photo-induced force microscopy. In Pipham, we use two mechanical eigenmodes of the AFM cantilever as two independent force sensors to measure AFM topography and photo-induced sample response concurrently. In order to keep the tip close to the sample surface, we operate the AFM with a small dither at the second mode F1, which has a force constant in excess of 1000 newtons per meter. This is shown in the middle panel. The sample is then excited by a tunable laser to vibrate the first mode F0 via photo-induced force. This is shown in the left panel. The laser is modulated at frequency FM, where FM is the difference between the second and first resonant frequencies. The laser modulation will produce a modulated photo-induced attractive force between the tip and the sample at the same frequency. At the same time, the force is also modulated F1 since the dipolar force is a sensitive function of tip sample distance. These two sinusoidally varying signals will mix to produce two sidebands, one of which will fall on the first resonance of the cantilever. The greater the attractive photo-induced force, the greater the measured signal F0 will be, as shown in the rightmost panel. This sideband detection measures the gradient of the photo-induced force and is characterized by sub-10 nanometer spatial resolution and excellent surface sensitivity. By using two lock-in amplifiers, both the standard AFM and the photo-induced force data can be acquired concurrently. At a fixed excitation wave number, Pipham generates a map of absorption strength for dielectric materials at that wave number. At a fixed location, the laser can be tuned across a spectral range to generate a Pipham spectrum, which correlates well with the bulk FTIR spectrum, provided the sample has no nanoscale inhomogeneity. Here, the nanoscale Pipham spectra are compared to the bulk FTIR spectra for several homogeneous materials: nylon, polyethersulfone or PES, or polymethyl methacrylate or PMMA, and polyimide. We can see that the agreement between the Pipham and FTIR spectra are excellent on these homogeneous materials. For this slide, we took a Pipham spectrum on a homogeneous piece of polyvinylidene fluoride and used an online FTIR database to look for a match. The first match with the highest quality index is polyvinylidene fluoride. Since Pipham has excellent sensitivity and can acquire good spectrum from defects as small as 20 nanometers, it can identify unknown defects with good confidence. In samples with nanoscale inhomogeneity, we should not expect a good match between the bulk FTIR spectrum and the local nanoscale Pipham spectra. In this example, a laser toner particle, which consists of multiple components, is ground to acquire an ATR FTIR spectrum as shown in red. A whole toner particle, which is about 7 microns in diameter, was glued down onto a substrate, and 3 spectra were taken at different locations. In this case, we can see that the bulk FTIR in red consists of spectral features from the 3 nanoscale Pipham spectra. Location 1 in yellow contributes primarily the peak near 1100 wave number, whereas locations 2 and 3 contribute the peaks near 1460 and 830 wave numbers respectively, along with many other common peaks. For samples that have nanoscale inhomogeneity, a Pipham spectrum will represent the local chemical state, whereas the bulk FTIR spectrum will represent the sum of all the local chemical states. To determine the spatial resolution, we like to use a polymer, which has a well-defined distribution of chemical components. In this PS-PMMA polymer, with a full pitch of 22 nanometers, each chemical component is about 11 nanometers wide. When we set the excitation laser to 1493 wave number, which is a strong PS absorption band, Pipham highlights just the PS molecules shown in red. When we repeat the measurement at the same location with the laser set at 1733 wave number, Pipham highlights the PMMA molecules in green. We can then combine them to create a chemical map as shown at the far right, where green and red regions represent PMMA and PS molecules respectively. If we look at the area in the white circle, we can see the PS contains a finger-like structure, whereas the PMMA contains the pocket structure for the finger. Looking at the cross-section in the PS image, we can see that the 10% to 90% transition is about 6.5 nanometers, demonstrating Pipham's sub-10 nanometer spatial resolution. We demonstrate the excellent Pipham sensitivity by characterizing a self-assembled monolayer film of octadecyl trichlorosilane, or ODTS, that is formed on silicon dioxide substrate. The substrate is a linear grating with varying width and spacing to test the effect of geometry on the packing density of the SAM layer. The structure is coated with 30 nanometers of silicon nitride and 5 nanometers of silicon dioxide on top of which the SAM is formed. When we image the sample using the CH stretching mode at 2917 wave number, we see consistently stronger signal at the lower surfaces compared to the upper surfaces. When 18 spectra are taken across the structure, we can see that there is a good repeatability in the spectra within the upper and lower surfaces, as is observed in the Pipham image at 2917 wave number. The spectra taken in the lower surface has much higher peak at 2917 wave number compared to the spectra taken in the upper surfaces. This indicates a denser packing in the lower surfaces. We attribute this difference in SAM packing density due to the different nature of silicon oxide in the upper and lower surfaces. Those interested to learn more can access the recorded webinar on the topic of nanoscale analysis of advanced patterning processes using the link provided. Here, we have a cross-section sample that contains polymer interfaces. The colored image in the middle is a composite chemical map which combines 3 Pipham images taken at wave numbers associated with the strong IR peaks for the 3 different materials. In the composite image, there is a relatively sharp transition from epoxy to P-degda, colored as green and blue respectively. There is a gradual transition between P-degda and SDIB layers, colored as blue and red respectively. It signifies mixing between these 2 components. To understand the local chemical state, we have taken 30 spectra across the interfaces with 10 nanometer spacing between each spectrum. Looking at the strong carbonyl peak at 1734 wave number, we see a sudden increase between spectrum number 5 and 6, consistent with the sharp interface between the epoxy and P-degda layers observed in the chemical map image. We then see a gradual decrease in the carbonyl signal strength from spectrum number 13 until it reaches a steady state level at about number 20. Again, consistent with the gradual change in color observed in the chemical map image. We can see that each spectrum displays gradual changes in the 3 peaks used for chemical mapping, indicating that Pipham can measure local chemical information with at least 10 nanometers spatial resolution. In this slide, we show that Pipham works equally well with organic and inorganic molecules. We're looking at a PS-PMMA block of polymer that has undergone a process called Selective Infiltration synthesis, or SIS. In this case, PS-PMMA block of polymer is exposed to a vapor of trimethyl aluminum, or TMA, which gets incorporated selectively into PMMA block. TMA is then converted to aluminum oxide by subsequent exposure to water vapor. This sample has undergone 3 cycles of TMA and water vapor exposures. On the left pane are shown the PS-PMMA block of polymer before the SIS process. As expected, the PS and PMMA blocks show similar block widths. The red and blue spectra below show Pipham spectra on the samples before and after the SIS process respectively. The red spectrum shows the expected peaks from PS and PMMA, while the blue spectrum shows new peaks at 1029 and 900 wave numbers, consistent with peaks associated with aluminum oxides. On the right pane are Pipham images for PS, PMMA, and aluminum oxide at their respective wave numbers, along with the AFM topography. We can see that the PMMA block has swollen due to infiltration by aluminum oxide. The Pipham images for PMMA and aluminum oxide are well correlated, confirming selective infiltration into PMMA blocks. Looking at the cross-section profile of PS chemical map in green, we see that the PS block now measures about 9 nanometer in width, shrunk from 21 nanometer in the pre-SIS sample. The 10% to 90% transition for the PS block now shows about 5 nanometers, which demonstrates the exceptional spatial resolution of Pipham chemical maps. More on this application on directed self-assembly is provided in the link. In this slide, we share an example of visible Pipham where changes in absorption due to ionic migration in a perovskite photovoltaic film are observed. The excitation laser is set at 650 nanometers. Following the yellow arrows, the stress voltage labeled as SV in the cartoon diagrams are changed from zero bias to -1 volt, then subsequently changed to positive 1 volt in steps of 0.2 volts. Going from 0 to -1 volt, corresponding to figure A, and the first 2 Pipham images, the accumulation of the cations on the surface increases the absorption greatly. As the stress voltage is decreased from -1 volt to 0 volt in 0.2 volt steps, the electric field that holds the positively charged ions gets weaker and becomes less effective to maintain the surface cationic species. Consequently, some ions drift back into the deeper region under concentration gradient, leading to a decrease in both the Pipham signal intensity and absorption areas. These are shown in Pipham images 2 through 7. When the polarity of the stress voltage is reversed, corresponding to figure B, the organic cations are driven away from the perovskite surface area by the electric field, which in turn further reduces the absorption intensity, now shown in Pipham images 7 through 12. The last image at +1 volts is similar to the original image at 0 volt, suggesting that the electric field-induced ion migration in the perovskite film is almost fully reversible. This shows that visible Pipham can effectively measure the performance of the photovoltaic film and complement the chemical understanding of the photovoltaic materials that can be gleaned from IR Pipham. This table summarizes the current landscape of common analytical techniques. While elemental information can be acquired with atomic resolution with electron microscopes, we can see the glaring gap in the current molecular analysis below the spatial resolution of about 200 nanometers. Given Pipham's spatial resolution of sub-10 nanometer and monolayer sensitivity, Pipham fills that gap very nicely. Our contact information and our website are listed here. Thank you for your attention.